So, rotational momentum. Now, we talked about rotational energy. We've talked about rotational motion. We've talked about all these things. And the only difference between rotational momentum and linear momentum is that we're using the rotational terms for the linear terms. Okay? So, if you remember, momentum in itself is nothing more than mass times velocity. So, when we talk about rotational momentum, we're talking about the same thing, but just the rotational equivalence of it. Okay, so it's a really simple idea. So rotational equivalence of mass is what we call rotational inertia, which is an I, which is a really fun looking I. There we go. Okay. And then the rotational equivalency of velocity is omega. Angular velocity, angular frequency, angular, what was that on? Rotational frequency, velocity. Okay, so this is what we call rotational momentum. It's rotational inertial value, which for a point mass is mr squared. It puts a lot more equivalency on where the mass is located instead of on what it is, how much it is. And then the value of how fast it's spinning. Now, like linear motion, and linear momentum, when we talked about conservation of momentum, rotational motion has the same equivalency. We can talk about linear motion being this conservation of momentum, the initial value equaling the final value. Okay? Remember, P is my unit, or is my representation of momentum. In rotational equivalency, it's L. Okay? So when we talk about linear momentum being conserved, we can talk about rotational momentum being conserved. Same principle, nothing different. It's just instead of linear motion, rotational motion. Now, why is this important? Well, several things. I mean, the first one is the one that's most talked about, and that is the figure skater. If you ever watch figure skating, you see figure skaters with their arms out way tight and they're going really, really slow. And then they want to speed up. They bring their arms in. And then they go, woo, spin like a top. Okay? That's conservation of linear momentum. Or not linear, of rotational momentum. Here they have a high inertia value, high rotational inertia. They bring their arms in. This value goes up, or it goes down, so this value goes up. So you can say that the initial rotational momentum is times the rotational velocity is equal to the final rotational momentum times the rotational velocity. So here's the arms out with a high number, and this is a low number. When you bring your arms in, this becomes a low number, that becomes a high number. So you see the figure skater spin even faster. The other way in which you consider rotational momentum is flight. When you're traveling through the air, right, you're pushing air. But what we know is that as air is being pushed, the air spins. It's what we call turbulence. You try to reduce the turbulence, but you're never ever going to get rid of it. And it's believed that that spinning motion puts a spinning motion on the wing. It forces the wing up when it spins. Okay, so it's applying this spinning motion, and once you apply all that spinning motion across that wing, there's a net push up, even though there's a little bit of a tilt. There's a pulling of this way. Okay, but most of it is pushing it up. And that turbulence is the reason why you have lift. The spinning motion as it goes down the wing creates the wing trying to spin. But because of the mass of the wing, it's obviously not going to do it. But that's the principle behind it. That's why rotational momentum and the conservation of momentum, of rotational momentum, is so important. I mean, those are just some simple things. Okay? It's also, you know, when you talk about the gyroscopic motion, when you talk about satellites in orbit and how they adjust themselves is by changing the rotational momentum. There's a gyroscope spinning in there. If you apply any kind of force to try to change that rotational momentum of that gyroscope, it ends up moving the craft in the opposite direction. Okay, so if you have it this way, and you apply a force to try to change that momentum, so it's spinning this way really fast, and you try to slow it down, it ends up spinning the satellite. It changes its motion. So depending on whether you're changing the gyroscope this way or gyroscope this way, you can tilt that satellite in any direction just by applying that force. Now, you apply a force to speed that object up again, and you can stop the spinning motion of the satellite. So you're just adjusting it that way. It's pretty brilliant if you think about it. But that's all conservation of rotational momentum. So in one simple video, because it's basically momentum, which you've already covered, rotational momentum and conservation of momentum are ideas you've already dealt with. So there's nothing really brand new about it. Okay? Cool? So momentum, rotational, I should say.